Good morning, everyone. I would like to thank the organizers, the leadership team for inviting me to give this talk. So, hello. Okay. So, already we saw a lot of introductions, so I don't have to get into detail. So, I am assuming you know about the magnets. I'll talk about some of the parameters so you can reach out to me. So, I'm going to touch on within a short time conventional magnet manufacturing processes, and I will talk about additive manufacturing we worked on last 10 to 11 years with Ikena and current status on printed magnets, future directions, and summary. So we saw already the slides, and you can use all these magnets in different things. So the critical minerals, we know neodymium and dysprosium and cobalt are these things. Only two strong magnets, samarium cobalt, we saw that neodymium and boron. So our goal is, if you want to do manufacturing, the thing I want to talk about, Brenton talked about intellectual property. The IP is the key thing because we cannot just like that. We can work on, do research, but if you want to manufacture, Hitachi controls most of the patents and all those things. So that's where we want to come up with our own manufacturing methods. Like June is working on a lot of manufacturing, like hot roll methods. So we do. So these are the challenges we face. So it doesn't matter. We talk about recovery, all these things. Finally, manufacturing, we need IP to do that. And we want to work on like dysprosium free neodymium ion boron. We saw the high temperature operation with the dysprosium, it goes up. But you can also replace it with copper and aluminum. So that's a new research like the grand boundary diffusion. So you don't really need dysprosium. So you can actually replace it with copper and aluminum. So that's another process. Or you can use samarium ion nitride and the cerium cobalt. That discovery came through Andre through CMI. So that's another different composition. So iron nitride, so I will touch on some of these things. So when you manufacture yourself, so you can mix and match. So that's where the opportunity we have based on the temperature of operation and the field and the condition, you can change. So this is a plot. We already talked about all these, June talked about the saturation magnetization. Right here is plotted with the Curie temperature and the size is the energy product. So the larger the size, you can see the energy product. So you can actually see the neodymium ion boron is right here. So it's 312 and the Kelvin scale close to 600 Kelvin. So that's where the neodymium. So if you really want to use high coercivity, you have to go to Alnico or samarium cobalt or some of these magnets. And the feature is like iron cobalt, iron nitride, samarium iron nitride. So these are some of either critical rare earth free transition. So the iron is the critical component. So if you need to make cheaper magnets, you need to be closer to 65 to 70% of iron. That's a key component for anything. Then you have the rare and all those things. So let's touch on commercial magnet manufacturing. So the sintered manufacturing process, like Ryan gave an excellent talk at the PMS meeting last month. So neodymium, dysprosium ion boron, or samarium cobalt. So I'll touch on bonded magnets. So there are calendaring, injection, expulsion, and compression molding. And then we'll touch on some additive manufacturing. So like last year, June started this effort and Ryan and I were part of it. So we have like 2 review articles in the JOM. So you can actually look at the details of permanent magnet, part 1, sintering and casting, and all the emerging bonding methods. So this is a very good reference. So you can actually go and see the current state of the art of manufacturing processes. So it's a good reference to see. So let's look at the sintered magnet manufacturing. The thing you talk about 214-1, neodymium 2, iron 14, and boron 1. So that's the composition of 214-1. And you are going to start with the strip casting. So it's basically you are casting and rolling on a big rolling. It's a roll, heater roll, and you are making this strip casting. And that's the very first step to make anisotropic magnets. So one thing what you want to do is high performance magnet is you want to be anisotropic to be present in the magnet. And once you do the strip casting, the next step is hydrogen decryptation. So that's a really good process. You just take a magnet or even this cast material, and even hydrogen, just in room temperature, it will crumble into powder. So that's a good thing. So even if you want to recycle magnet, that's what you would do. Sometimes broken magnet, you can take a magnet, anneal and hydrogen, it crumbles into powder. Then you do a warm annealing, like it will form like hydrides, it will come out. So you can actually recover the magnet powder and you can go manufacturing. So the next process will be jet milling. So you are just grinding and then speed and all those things, different process. Then once you have the jet milling and the powder size you need, what you are going to do is you are going to align it in a magnetic field. So you are aligning like pressing, more like compressing and going through the sinter and treatment. So the heat treatment process is here, long duration time. So very slow duration. Then you will do the dysprosium and terbium, and it will be a grind boundary diffusion. So that's the process, may take a while. Then once you make it, the way magnets are made is they are making large pieces, like huge. Like that. Then once you have the magnets made, then you are doing the machining. So the machining is done. That's where a lot of every step, like from the strip casting, hydrogen decryptation, jet milling, you are going to sieve it and particle size variation, pressing magnet. Every step you will have some wastage. So that's where we are looking at some how to recover some of this critical mineral materials from this wastage. And if you are even efficient process, it could be only 70%, 30% you may see is a wastage thing. Then once you do the machining, again, you are cutting into ring magnet, small size and shapes and all those things. Then the plating is, we saw already, John talked about. So the nickel, copper, nickel is the standard thing. So you have to coat it with nickel or copper, or nickel, copper, nickel. So the coating is to prevent oxidation. So otherwise, this rarer, the iron will oxidize. Then finally, you do the final magnetization. So that's where all this north and south pole you are going to do. So it's a long process. So this process is, but you can make large quantity, but the IP is a challenge. So you're going to run into thing. So similarly, if you want to look at samarium cobalt, so samarium cobalt has two compositions. One is 1,5, samarium 1 cobalt 5, or 217. So you will see there's two methods thing. So what you are doing is, again, you are starting from the raw material, and instead of cobalt, you may also add iron, copper, zirconium, and you are doing the induction melting. It's a pure metallurgy, so you do the induction melting, then crushing, and do the ball milling and small powders. Then finally, you have again the temperature conditions we talk about, sintered magnets. You go through this high temperature and slow cooling and two-step reaction, annealing and punching and all. So these are two compositions you do. Then finally you do the pressing, sintering and grinding and magnetization. So that's like a standard process you can do. And once you make the magnet, so these are something like this. So one good thing about samarium cobalt is it's a high temperature, high Curie temperature. A lot of aerospace applications, they prefer sensors and all those things. They prefer samarium cobalt, even though it's a little bit weaker compared to neodymium and boron. And you don't need for strip casting the starting process. So it's a simple and no need for coating. And the sintering and heat treatment is fairly good, easily reproducible. So these are standard process compared to samarium cobalt. So someone asked about bonded magnet. So the first thing you can think about bonded magnet is the refrigerator magnet. Every house you have something on it. And so that's a bonded magnet. So the way it's done is you are mixing with the polymer and cast on a sheet, or they can do it on a plastic, and even with temperature, they magnetize on one direction. So we'll talk about the magnetization step that will come once you print the magnet. So that's why if you know the refrigerator magnet, it will stick to only one side. So they magnetize hallback array such a way it's magnetized on one direction, only one side. The other side won't stick to it. So that's a new thing. So that's where they put the air and all those things. So there are different kinds of polymers. No. So the thermoset polymer is like you can just nylon is a simple, or polyethylene, the ones we use for grocery bags and all those things, polyethylene, polypropylene, containers and sheets. So those are all thermoset. So thermoset is, sorry, so That's the compression. That's a resin, more like a resin powder. So you can mix the resin for the process. So if you want to make a rigid, really not flexible, rigid product, you use the compression molding. Thermoplastic is the, sorry, that's the nylon. So the injection molding is very simple known. I will talk about the process in the next slide also. So if you want to do the extrusion process, you can do extrude through the nozzle and do filaments. Elastomer is, that's the one flexible magnet. So the one we talk about refrigerator. So these are different kind. Either you can make a rigid, flexible, or thermoset, thermoplastic. So each method may dictate how loading you can do, because already June talked about if you reduce the dysprosium, you're going to again add more, the magnetization, all those things may really go down and all those things. So the thing people always get confused is volume fraction is related to the remnants and the energy product. So BH max, we know. So the compaction, compression, bonded, extrusion, injection, and all those things. So every polymer, based on the viscosity of the polymer, because some polymers may be highly viscous, then you cannot load more magnet powders into the polymer. The higher the viscosity, less. So if you go to PPS, you can do only polypropylene sulfide. 61% is the thing you can do. Or as on the polyamide nylon, you can do 65, and the energy product will go down. So one thing I want to talk about volume versus weight percent. So the weight is, there is a huge density difference between a polymer and a magnet. So magnet is a heavy metal, 7.6 grams per centimeter cube, whereas polymer is close to 1. So you are mixing a two different density difference between a polymer versus a magnet. So for making bond and magnet. So when I say like 80 volume percent, here we are talking 96.78. So almost 97 grams of magnet. So if you take 100 grams of a magnet composite, so you have 3 grams of nylon polymer and 97 grams. So that's where, when I say volume versus density, sometimes people confuse. So the volume is better, and the conversion rate is, the energy product is directly proportional to the magnet volume, square of the volume fraction. So let's say you have a 70 volume percent of a magnet. 70 volume corresponds to 95 grams. So 95 grams of a magnet are 70 volume percent. So 70 square. So if the starting magnet powder is 40 MgOE equivalent powder, you will end up in 20 MgOE, 0.7 square. So the starting magnet decides your bond. So that's where the challenge is, how much you can do the loading with this manufacturing process or any of these things, and how far you can do. So there are advantages. So the advantages is you can make like complex shapes and sizes. So we talked about sintered magnet, because you make a block. By the time you make a near net shape, like a ring magnet or any other different hard shapes you need in a motor, every time you are going to machine it. So the moment you machine it, you have a wastage. And the other thing is tooling. So the injection molding, you will talk about injection molding. Simplest thing is, you can think about Christmas cookies. The Christmas cookies, you need a mold. So without a mold, the shape Christmas tree or any other shapes you need. So that's what it's called a mold. Here you need a shape, and you are extruding into the injection and this thing. We have been doing almost for a century now. It's a standard process, but the loading is limited. And also the binder can provide mechanical strength. So sometimes the stronger the polymer, it can provide. Sometimes there are still challenges compared to sintered magnet. Brayton talked about sintered magnet is strong, still it's strong. But you can add like strengthening agents into this modern magnet. Or other things you can do bimodal particles. So you can vary the particle size, improve the pack intensity. The disadvantage is you are diluting with a polymer, and you are losing the energy product by square of the fraction. So you are losing very significant. That's a challenge when you use a bonded magnet. And the operating temperature again depends on the polymer. Sometimes if somebody needs, they come to me and say, I need a magnet that can operate at 500 degrees Celsius. You can do it. You can use a ceramic binder and some air cobalt, or you can use a sinter. So those are possible. And the tooling can be very expensive. So let's look at the injection molding, how they make. So the ferrites, it's easy, the ferrites is possible, and blends of magnets. So that's where the advantage we can make like hybrid magnet. So you have a design in a motor. So you want high grade at certain areas like edges versus center. So you can do gradient magnet. So you can do all those things using the opportunity with this injection motor. A lot of the like car parts, except the motors as well as the music system and all the thing, everything is made of injection molded or magnets. So the nylon like polypropylene sulfide PPS or polyamide 6 and 12. So these are standard binder types used in nylon. So you can make actually complex shapes, and the operating temperature can vary 40 to minus 40 to 180 degree, no post finishing. So a lot of times injection molding, once you make it, it's very fine surface. You don't need to polish it or any of those things, but you are limited by the low and the high tooling cost. So if you really want to make an injection molded magnet, the tooling can cost almost $100,000 to $500K just for the tooling. So unless you make millions of magnet pieces, the tooling is very expensive in the case of injection molding. That's where we talk about additive manufacturing or 3D printing. You are using a CAD drawing, you are completely getting rid of the mold. So that's and the mechanical properties can be better. So the compression molded bonded magnet is, so instead of mixing with the nylon or PPS and make it a composite, I'll show some pictures. You are using it with the resin. So you take a magnet powder, mix with the resin and press it in a press with a magnetic field. I'll show the picture in the next one. Epoxy is a thing. But you can make only cylinders and simple rectangular shapes, arcs. So you cannot make complex shapes using compression molding. And you can do higher loading compared to the injection molding. So 80 volume percent, but low tooling cost because you are using simple shapes and all those things and the mechanical properties thing. So we always look at is it possible to reach the properties of compression molding using additive manufacturing or beyond? So that's a challenge we were posed when we started working on CMI as part of the project. So here you have the different processes. The calendering is like you are calendaring, mixing into rolling into a sheet, just like we talked about refrigerator magnet. Or if you want to do the injection molding, so the injection molding is the molding and the tooling is the expensive part where it's twin screw extruder, it's molded into and making the part. So it's heating. So it's all done at a higher temperature. So the whole idea is you have to go close to the melting point of the polymer and mold it into the magnet and pull it out. Or the extrusion bonded magnet or compression bonded, where you are using a press under a magnetic field and it's a simple process. And June has again published and you can see all the details after that. So once you make a magnet, so we saw sintered magnet go through this process or the bonded magnet, then you have to do the magnetization orientation, like axial magnet, multipole magnet. So if you are really a mechanical engineer with motor, you will know all these things, multipole magnet, north and south pole, different direction. So the way they do is they'll have the fixture. So you take the machine or the magnet, you go through this. So every magnet doesn't matter, either it's sintered or it has to go through this magnetization procedure. Or you can make this hallback array we talked about. So this is using some other printed magnet. So you can see the magnetized direction is everything by like 90 degrees and you can make the whole thing. So you can actually make a magnet either a strong side or a weaker side. So you can play with this magnetization field and you can do all those things. And one thing we talked about magnet to magnet replacement. So if you do any of these new processes, additive manufacturing, so there is already Aichi Steel, Toyota, what they have in the market is, so they use the same rotor. So the rotor it's the same, whereas, the stator is same, but the rotor is made with 3 different magnets. So if you really want to replace the sintered magnet with a printed or a bonded magnet, what you need to do is you have to redesign your rotor. So that's the thing they have done. The stator is same, the rotor shape is different. So they have used sinter, MagFine, their injection molded, their compression bonded, and the magnet compared to sinter magnet, you may need more magnetic material with respect to injection or compression bonded, but with respect to the cost and the weight, it's going to be efficient. So really, if you want to replace some of this sinter magnet in a motor configuration, so you have to redo the rotor configuration. That's necessary. So let's talk about additive manufacturing. So how we can, so we saw the injection molding, compression molding. So a lot of times the best thing will be to powder metallurgy, like a selective laser heating. Can we use a laser powder bed to do the powder bed process, or cold spray and polymer additive? So I'm going to talk about some of these things. So if you come to like MDF, there are a lot of like 3D printing is going really strong. When we started like 10, 11 years ago, tabletop printers. Right now, imagine the printers are so huge. So you can even use fuse deposition modeling. You can print houses right now. So the future is you will be printing a plane. So where you don't have any connection. So that's a weaker. For every joint, you have a weaker. So you could potentially print. That's the feature of how this metal additive and using a binder jet. We'll talk about some of this process and things are changing. And again, GE jet sand molding. That's another thing. Instead of CAD drawing, sand molding is you can make a large sand molds of this whole size of this room, and you can cast and you can make magnets out of it. So these are things are changing, like soft magnets versus permanent magnets. So the icon flexes, if you look at the 3D printing houses, you can mix with this ceramics versus again polymer, you can do all these things. So when we started working on metal additive, for all the laser additive process, you need a spherical particle. So the moment you go to spherical particles, mostly you will end up in isotropic magnets. So the isotropic magnets are very weak. So that's why we cannot do right now really thing. And initially ABB worked on some of these things and they worked on, and we have done some work also. So you are going to make like porous magnet, and there are some improvements they are making, but it's not there yet. So it's still weaker magnet. And the moment you hit with the laser, any of the magnet powders during printing, the temperature like the 214.1, the structure decomposes. It becomes lose the coercivity, it becomes a soft. So that's why you cannot heat it to dissolve, like it really reacts. So that's where what we thought was maybe can you look at a lower temperature. So the cold spray is another additive manufacturing technique people use for aerospace, like all the planes, if there are cracks in the plane, they use the cold spray to really seal all the joints. So it's like a high speed with a nitrogen helium gas, you can take the powders and go through this and deposit at high speed. And you can, NRC actually, Canada, they made some work on that. And we also work with United Technology in a very long time back, made this thing. So here you will be using metal as a binder. So if you really need a magnet with a metal binder, you can get very strong magnets out of it, but it will be a very weaker magnet because you are diluting with the metal polymer. Instead of polymer, metals you are diluting, and also you are using spherical particles. So those are some of the challenges you are running into. That's why nobody has made further. And the other thing, some of you may be familiar with binder jet. So the binder jet, it's more like an inkjet process. So you have a powder bed and you are doing layer by layer with the thing. Here you are not limited to spherical particles. So you can use non-spherical needles. A lot of times anisotropic magnets are needle shaped, different shapes of particles. So you can use those things and use a resin layer by layer and heat treat and do all this process. So you can actually make this, once you do the printing and curing, depowdering, you can make like complex shapes. And the other thing in this binder jets, you will end up in 50% density. So you don't get the full density magnet after that. So what they do is they infiltrate bronze. So we have done in the past also, the moment bronze infiltration, you have to go to again 1050, then the neodymium iron boron decomposes. So there are challenges again with those things. We did some binder jetting process in the past. So we did make like 2016, made like sintered magnet and ring magnets. We compared the properties. So it's like 50% dense, 45 volume percent. So it's a weaker magnet, but you can still make binder jet process as a method for making magnet. Then we also did some infiltration using like different alloy composition, praseodymium and copper, some of the alloy. So we could improve the density of the magnet and remanence and coercivity. I think the remanence will decrease a little bit. So there are things you could do with this thing. But I would say the binder jet method or a laser jet method is good for making soft magnet. So if you want to make like iron silicon or iron cobalt or any of the other soft magnet, you could use metal additive and you can make like large sizes and shapes. So I'll show some examples. So then with time, what we started doing is we use this big area additive manufacturing. This is the fused deposition modeling. So this is an example. You can take the magnet powders, mix with this nylon powder. So it's instead of a filament, you have a chopped pellets, small pellets of these pieces. So mixed with this magnet with the nylon powder. Once you have a pellet and you can print this large deposition. So like in fact, Oak Ridge demonstrated large turbine blades. So like almost you can make like different sections. So you can do like 80 meters long process. So it's a huge process. So we made like sizes and unique shapes and sizes and properties. I would think we won R&D 100. We published a lot of papers based on this method. So you can see actually the video of printing. So we are printing a lot accident. So once you do this printing for measuring the mechanical properties, some of you know, to sensor. So you can do like fast. So you can do like 80 kilograms an hour. So you can do fast printing, but you may lose the surface. So you have to polish it a little bit so that then you can get on. So one thing with this extrusion process, we saw the microstructure magnet. That's the key when you coming down to the micron size. So the microstructure is very important. So if you look at the SEM where the particles are in a polymer matrix, so you have random. But during the extrusion, even without applying magnetic field, you see some alignment because of the alignment during like extrusion. So you see some improvement properties. So we use the starting like injection molded pellets and we did 3D printing. The properties were better than injection molded. That's where we have to look at this microstructure, this alignment in certain directions. So these are possible features, like you can align grind alignment during printing. So that's something you can do. And we worked on some of this process. So the feature is a robotic presentation. You can do again printing, you can do large scale printing and followed by compression molding. The way it's done is you do a printing and the printing is layer by layer. You are using a CAD drawing and printing. So when you do layer by layer, we are not doing anything pressing in between. So there are some porosity in the magnet. So even 5 to 7% porosity can reduce the properties. So if you compress it in a press, then you are, while it's hot, you can still, before it's cooled, you can really improve the density by 5 to 7%. And you can get like, so the new method we call it, I told, which is additive manufacturing, compression molding followed by. So that's a process we have been doing very lately and getting to property. So the way we work is we work with Ekina and this team. So we print the magnets. So the as printed magnet, if you look at the magnetization, so the as printed magnet is really a little bit weak. So good thing about this thermoplastic is you can go back and reheat. So anything with a nylon or PPS or polycarbonate magnet. So you can print a shape or size or anything you print. You can anneal it under a magnetic field. You can heat it and apply a field. So when you already apply a field and improves and you see the saturation and you can see the PR, remanence, coercivity and the energy product, you can see go from the 4.4 MGOE all the way to 17 to 18. So all these post-magnetic field annealing. So that's the challenge we have when you want to make large printed magnet. You can print magnets, but the post-magnetization. So we have done like small sections like 2 by 4 by 6 into a magnetic field. So that's something you have to do. Like you can do annihilate and do that. And if you look at our progress when we started 10 years ago, so the energy product was right here, and we are close to like 23 to 25. So our goal was 25 NGOE was the gap magnet compared to either samarium cobalt or neodymium iron boron. So imagine we doing our process, we have the IP, we have the printer company manufacturer. So these are advantages what we have and what we can do. So we need to look at the properties what we have with the printed magnet. So if you look at the properties of this additively manufactured magnet, these are better than commercial like injection molding or compression molding, but not as good as sintered magnet. So we do lose some energy products because of the dilution with the polymer. But the resistivity is 3 times higher. Even the 52 MGO is sintered magnet. So if you take the printed magnet, the resistivity is high. Because of that, the eddy current loss is almost 0. So that means even if you don't need, like when you have a sintered magnet in a model configuration, I'll show some example. You have to again machine it, you see some wastage while cutting. Whereas here, the eddy current loss is almost 0. And the other thing, I'll show a slide where recyclability, because you can recycle very easily some of these magnets. We'll show an example. And the corrosion resistance. And June talked about all these things, mechanical properties, energy product. So it's not just one thing. You need to have coercivity, remanence, and the recyclability and the cost and all those things. So here, very recently, we worked with Kina and the team. So the bimodal particles. So one thing we talk about neodymium and boron, you can packing density, it's not going to be very high, like 0.6 to 0.7. And if you mix it with the samarium iron nitride, so that's where we do all these things like the bimodal thing. You can take like dysprosium-free neodymium iron boron mixed with the samarium iron nitride. Samarium iron nitride magnets are made 3 to 5 micron size, small size particles. Neodymium iron boron is always 45 microns or higher, so almost 100 microns. So if you take neodymium iron boron, you try to do any grinding down to small particles, it's highly reactive, it's very unstable. They don't even make fine particles of neodymium boron. So it can catch fire at night, so you will run into problem. So that's where here we can mix like this samarium iron nitride with this. So this is an example I'm showing, but you can use with any other magnet compositions, and you can use this process. And you can see like packing density, and you can improve, and you can anneal, and they improve the mechanical property. So these are advantages we have when we do this printed magnets. We can do post magnetic field annealing, and the energy product is close to like 22 to 23. And you can see when you heat it to higher temperature, it may lose all those alpha, beta we talked about. And if you look at the mechanical properties, still it's weak, I would say. Like nylon, you are 6.6 MGOE, the tensile strength. PPS, you can go to 20. Sintered neodymium iron boron is 80 MGOE. But you can add some additives where we have looked at the carbon fiber addition. You can improve against strength. These are things you have to improve on some of the printed magnets. And the other thing, this is the one we talk about eddy current loss. So if you look at the resistivity of this sintered magnet versus thing, the resistivity is really almost 2 orders, 150 micro ohm versus 170 milliohm, because you are diluting with a non-conducting polymer. So that's why you are reducing the resistivity of the printed magnets. Whereas the eddy current loss, you can see almost it's down to 0, whereas the best magnet has a very high eddy current loss. So the eddy current loss, as I said, is better compared to the sintered magnet, and the resistivity is higher. And the other thing, we have shown some thermal stability. Like you can take this neodymium iron boron and TPS, or nylon, this thing, you can actually take some of these magnets and heat it in air. So we have done like flux loss studies. Typically, the motor manufacturer, what they do is they take the magnet, heat it under like different temperatures for different time. So we have done like 2000 hours of heating. You can see less than 5% flux loss. So you have to have less than 5% loss of the magnetic moments. So that's the idea of the end. We have shown close to 4%. So these are different compositions, different polymers, different composites. We have shown something. So you have to, based on the application and the temperature, conditions, property, you can design your magnets and all those things. So that's where the future, I would say, like AI, ML could be, because there are a lot of data is available. So it could be possible, something where robotic manufacturing, metallic may look at some of those possibilities in the future. And the other thing is, I talked about recycling. Here, if you take the magnets, simple, you do a crayon polymer, because polymers crumble into powder. The whole idea, I forgot to tell you, is compared to cold spray or metal additive, the reason we went into a polymer bonded magnet is we are relying only on the polymer melting. So the magnet is still maintained, and there is no degradation when you go through this process. So you can really do it. And mostly we work with the non-magnetic powders. These are demagnetized powder. And once you do the printing and apply a magnetic field, so the magnets have memory power, magnetic power. So the moment you expose it to a magnetic field, it will align itself quickly. So you can do, that's where post magnetization, you can maintain the shape. So you can take this and you can remanufacture all those things we have shown in the past. And this is an isotropic magnet. And very recently, we have also worked on an isotropic magnet and still under revision. So these are opportunities where you could do. And you can also use the same process for making bonded magnets. Any wastage that's coming from the sinter magnet, and take some of those wastages, grind it, go with this process. So these are opportunities we have with this thing. And the other thing is we want to look at the LCA and TA, and we work with Professor Hu in Purdue and John Sutherland's group, and we have published some LCA work compared to like this case. So we are comparing with a sinter injection molder, and very recently we have also compared with the sinter. So there are again global warming and some of these things. It's actually better because of a lot of other properties what we have, and you can see more details later. And similarly, the TEA we published, you can see after 1 or 2 years, you can see the improvement in thing, because you have a huge investment in the beginning with respect to the printer. Once you have it, then you can use it. And so there are good opportunities there. So then you can do all these things. You are again in a technology readiness level only 1 to 3. Can we go beyond? Can we use a real mode? So that's where the interns come in. A lot of undergraduate interns, when they come for Suli and all these things, we take like real models and we really open up and take the existing, like this case was a ferrite magnet. We replace it with a printed magnet, and you work with the group where we can test this magnet. So we have a left side is the regular commercial motor, small 12-volt DC motors, and the right side we replace the magnet with a printed magnet, and you can actually measure the back EMF, and it's almost same as the good, and you can see maybe it's running motor something. So these are some of the things we did it with a 12-volt motor thing. So then can we go higher? So this one, like Christoph Lehmer, like in Switzerland, he made a completely 3D printed motor structures with a sinter magnet and the copper wire. So here what we did was we used the same CAD drawing, and we printed all the structures with a sinter magnet. On the left side, we used the additive manufactured magnet. And this is a brushless 600-volt motor. And we have measured some of the magnets are our B, even though 600 watt, then we moved up to 1000 watt. So these are things we are looking at. How do we go beyond higher grade motors? And and you can do the look at the testing of the 600 watt motor in a closed configuration testing and all those things. So these are things are improving. And very recently, like even one of the Tesla models, copper wiring has been known for centuries. We have been using simple copper wire. Now there are additively printed copper wires. So these are the features. So you can actually print some of these different models. So additive drives in Germany, they do. There are 3D printed like e-bikes are already available. So the feature is you can print some of the soft magnet using laser editing. So I'll give an example where we have already worked with on our magnetics. Here we use a iron silicon stator and copper wire we had it and printed magnets and we fabricated things. So here in this case, we showed only the permanent magnet and the soft magnet feature. You can also do the copper. So you can think of like completely 3D printed models are coming along in the future. To summarize my talk, so we have energy product somewhere close to 23.4, and the process methods outperform the injection and composite molding. And you can do the other challenges. We are doing post magnetic field annealing. What we want to do is we have done like printing and aligning at the same time. So we achieved only like 80% alignment during printing. So that's an area of research we'll be focusing in the future. And we aligning while printing, then you don't need the post magnetic. So we have demonstrated like 3D printed manufacturing. And thank you. I'll be happy to answer.
Thank you for the great talk. In the interest of time, maybe we can have one question. If we want to like draw the process flow diagram of bonded magnet and sintered magnet,
Yes.
will there be any common steps?
The starting powders is
The powder is same, right?
yeah, yeah. So the strip cast material versus the thing. So here the bonded magnet is again hydrogen depreciation, HPDN. So I would say those powders are good. So instead of going through the sintering process, jet milling, sintering, here you would use the polymer. Yes.
Since there is a portion of polymer in the bonded magnet,
Yes.
Obviously the energy product
Yes.
will be less
Yes.
for the bonded. Okay, thank you.
Yeah. But the other properties are better versus the thing because eddy current loss is a huge factor in motor and generator. And the other thing is near material, so you have less. So IP is another thing. So it's a okay, thank you.
That's all. Thank you.